brought to you by Collier Research Corporation, a company with over 20 years' experience in composite design, structural analysis, and optimization. Today's webinar will demonstrate how the newest HyperSizer product called HyperSizer Express can be used for general composite applications. The webinar will last 1 hour with 45 minutes of presentation and 15 minutes for question and answer. Please feel free to add your question in the bottom right of your screen. And our presenters today will be Craig Collier, President and Chief Technologist of the HyperSizer product, and Dr. Bertram Stier, Research Engineer of Advanced Composites for Collier Research Corporation. And at this point, I will turn it over to our presenters.
Good morning, everyone. Thank you for attending our webinar. You've had a moment now to see the first slide. Obviously, we are a company that started in 1995, basically as a spin-off from NASA. The software that you're seeing today has its beginnings from 1988 and was developed 7 years at NASA Langley Research Center. The engineers and software developers from NASA at that time started the corporation and remain principal developers today. So what is the software? Well, we need to say up front the software is not a CAD package and it's not FEA, but it indeed does couple with FEA, and that's for the purpose of capturing load distribution. And once we have made that coupling, then we perform the automated non-FEA and general failure analyses to determine optimum panel beam design and detailed stress reports. The process kind of begins like this, where we have the CAD surface geometry defined by the engineer, at which point an FEA or a finite element model is made. That could either be Nastran, Abacus, or ANSYS. And of course, the applied loads are also put on the model. The FEA solution is submitted. Element forces from that solution are provided in HyperSizer. And then as we optimize the different areas of the structure, we will then update the FEA model with stiffnesses and masses. And this is an iterative process until the loads converge, at which point we reach minimum weight. As you can imagine, being that we are from NASA, the software is specifically in the past devoted to the aerospace industry. As you can see here, in addition to AIAA, you can see key customers being aerospace. And that is a point I do want to emphasize. Of course, this is only a select few of the many aerospace companies we do have as customers. But at this time, let me go over here to the software and kind of show you the things that we do with it. What you're looking at now would be what we call very large optimization and stress analysis. So this is a 737-like integrated fuselage wing finite element model. And what you're looking at obviously would be, if I turn on the transparency view, you're looking at the internal ring frame floor structures. If I was to zoom in over here on the wing itself, you can see the internal ribs structure. You see in the stiffened panels basically throughout the aircraft. And that was the point I would want to make, is that the software's purpose has always traditionally been intended for aircraft construction, either metal or composite, where there's a need to analyze and optimize stiffened panels, as you see here. Now, if I come over here and I turn on the failure modes, this is some of the controlling load failure modes for the structure. If I right-click here, you can see all the stringer segments related to, say, the upper surface skin. And once I highlight one of those, then I can come to the software itself, and I can see, first of all, I can view the cross-section. So what you're looking at here is the layers that basically define the 0, 90, and 45s for the stringer itself. If I, of course, look over here to the left, I see the label and the optimum value, the dimensions for the stringer. More importantly, if I go to the failure tab here, you will be able to see literally hundreds of failure analyses the software performs. And I do want to emphasize the fact that, a lot of these are panel-based, so panel buckling, column buckling, crippling. Here we see force crippling, post-buckling, diagonal tension, compression, crippling interaction. You can go through the list here, geometry rules for the stiffener flange to height, ratio, limits, and then, of course, things related to bonded joints, pill stresses, interlaminar shear stresses, C-bush, pull-through bolted joint failure analyses, things of that nature. And you can also see in the software a lot of tabs here. So the point is it's really overbearing for the general composites community. Really great for those that are dedicated in the aerospace industry, perhaps not so great for those that want to do sandwich and solid laminate type optimization. And lastly, let me show, like from the tree here, one of the purposes of the software today is to track. So we have over 660 display sets that we can show in the tree here for basically this model. So we perform not only the optimization, but also the stress reporting for such a application. So let me take this back away now and go back to the PowerPoint. And what I want to talk about is about 5 years ago, we were working with a joint customer here on an internal nacelle for a jet engine, a thrust reverser. In the image to the right, you can kind of see the relative size of this part by the people making it. And you can see, obviously, there's no internal structure, so there's no natural boundary of where the plies should terminate. What are the locations of the ply drops and adds are completely open for the designer. Now, of course, the stress engineer is going to come up with a laminate stacking. May not necessarily be the optimum. But the tool that we developed was not intended now just for the stress engineer, but was also intended for the designer. Furthermore, the designer wanted to know, again, where the ply boundaries would be most optimum. Now, as a stress engineer, we would be looking at things such as the displayed membrane NX, NY, and NXY membrane forces, computed, these are the internal shell forces, the stress resultants. And from these plots, along with the customer, we tried to determine the best grouping of elements to assign to a finite element model property. In Nastran, that would be a P-comp or a P-shell. And we wanted to know what group of elements should have the same laminate. So what you do is attempt to look at the magnitudes and the gradients of each of these plots to determine the best optimum pattern. But one should also consider the bending moments MX, MY, and MXY, and the out-of-plane shear forces QX and QY. Then there's the issue of hundreds or literally thousands of load cases. And you can see it becomes intractable to manually establish optimum property zone patterns. So this was the beginning of the Express product to address this need for the larger composites market. Oh, and so the last image here is a representation of one of the attempts of defining what finite elements should belong to the same property card. So the software's intent is to address sporting goods such as bike frames, snowboards, tennis rackets, automotive, which we are going to do a lot of demonstration today, things like doors and trunks and body panels and things of that nature, medical, industrial, marine, wind energy, of course aerospace. When I say aerospace, I mean things that are not the large acreage structures, but things that are more like fairings or structural sandwich doors and winglets. So as we developed Express, we developed it to provide a software interface with just a minimal amount of data input and things to see for the end user. And we focused this product for sheet metal, laminate, and sandwich panels. Now, however, under the hood is the complete and verified analysis methods that you saw earlier, of course the non-stiffened panel ones. And we're including this in a powerful way for handling the composites, and that includes the material allowables and stress reporting, and as well the optimization capabilities. So in today's live demos, the first one we're going to show is a torsional stiffener. We're going to use the Nastran FEA to do this. We will begin basically with doing a very quick metal sizing, then we'll switch to a composite laminate sizing. In the beginning will be strength-only base criteria, and then we will add a stiffness criteria, essentially a deflection limit. The second example would be a kite board using Abacus, and then Bertram will give us a presentation of the bike frame. So kind of in reverse order now, the bike frame obviously looks as you see in the left image. The right image is from our website video. Essentially the story is that the nature of bike riding has changed, and with it the design and sizing of bikes. Modern bikes need to be stronger, stiffer, lighter, and more reliable. And that's to sustain the higher loads from the more extreme riding conditions, such as slamming into a signpost and doing a front flip trick. Well, this type of riding demands optimum use of the high-performance material. And you could say the same for the board industry, and it's regardless if it's a snowboard, kiteboard, or wakeboard. For each of these, you know, the image on the left, the guy, you know, he's carving, and the guy in the middle, you can see how high in the air he is. Obviously, the guy on the wakeboard is doing an aerial flip, and you can imagine that rotational inertia is an important part of the maneuver, so a light board is really a must. And for all these applications, lightweight, strong, and just the right amount of stiffness is expected by today's buyer. So the CAD image on the left is what you'll see in the live demo. That's the starting point after the model's been made. And you can obviously see where the boots are intended to be located. And the image obviously to the right is the fabricated part. It's a photo of that. And I will show you this again with Abacus. For the automotive example, what you'll see is, and this is our first example, by the way, the model is representing a real composite prototype part for a major automotive OEM. Due to the need to maintain the proprietary data, we are allowed to use and show the film, but we cannot associate it to the car company. So the image displayed here is one we found on the internet to represent where the part is located. The loading on the part is actually in plane shear, and the required stiffness is also in plane shear. However, the loading used today is an applied twisting that's constrained at 4 locations, and we will optimize this part first as a sheet metal and then as a composite laminate. We will also optimize the laminate ply stacking to strength to prevent failure, material failure, and then, of course, as you can see in the image, we'll impose a deflection limit. Now, a major point that I think is important to make it is that when we optimize this part of interest, we can do that, and then we can selectively update only that portion of the film. But when we submit and iterate with the FEA solver, it would be the entire FEA model. And that's because as you change the stiffness in this part here, you need to share load with the remaining part of the structure, and that can be done with the full-up model, or it could be done with some kind of super element representation of the full-up model. So the purpose of the software really then would be to give you an optimum solution under given loading conditions. And of course, these are the primary questions you want the software to answer for you. The first would be, what are the best potential boundaries of the Ply patches? And I'm referring again to the engine enter nacelle example I showed earlier. And then for those patterns, how many plies do I need? And lastly, what's the best fiber direction per ply layer? And we want to do that to meet both stiffness and strength throughout the structure to get the lightest weight. And of course, there may be a desire for you to consider to allow the software to show you where it's optimum to be a solid laminate, or what part of the structure should be probably foam or honeycomb sandwich. And if it's a sandwich, then what is the necessary core density in the different areas? And we do this extremely fast, and we do this extremely easily. So compared to the Pro product, you'll see a very minimized interface that has these green check boxes on the left-hand side to kind of status the progress that you make during the optimization. So with that, I'm done with all the PowerPoints that I plan to show today, and let me go ahead and take this away. And now I'm going to start the software from the beginning. So I go to the location where my model exists, and it's an Astran model. I'm going to select it here, and just for you guys that are familiar with the ASCII-based input file, this is the file. It's got some subcases defined. It's got your typical force cards. And as I go through the file, you'll see the boundary conditions and the P comps, and lastly the grids, and of course C quads are in here someplace. Well, they're down. They're at the bottom, I suppose. There they are. Nothing magical about that. So I will select that file. And what I'll do is use the Express Automotive database template. It is intended that, depending on your application, be an aerospace or wind energy or whatever, that you would use a specific template database because of the failure modes and things like that are pre-selected for that industry. So what I want to do next, you can see now a very simplified interface. I'm in the Fem import mode now. I want to select design mode. I want to go to metal. Normally I would hit Express import, but I want to do custom to allow you guys to see the steps. The solver is MSC Nastran. Here's that BDF we saw. It's on the associated OP2. That's the binary file of the stress resultants. Here are the load cases, the load sets that you saw in the ASCII file. The filter file would be used if we were using that full-up car model. We were going to filter out just that torsional stiffener. But in this case, the model is self-contained. You can go to different units. This model was actually defined in SI units, as you see here. And what I want to do is display in HyperSizer English units for it. So it's going to automatically convert the model from the SI units to English units, and then when it has to update the stiffness or the mass terms, it will then convert them back to the SI units for the FEA solution. So now I'm importing the model. The first time around, I don't want to include a solver, so I'm going to click that off. And by the way, let me come over here and orient it in a way that you're familiar seeing it. So I'm going to push this box over to the left. And this is basically, if you look at the mesh here, you can see the mesh like that. And I'm going to turn the mesh back off. And there's another icon here where we show the boundaries. So these are the boundaries defined by the engineer. So these are basically the grouping, if you will, of the finite elements to a preconceived notion of what an optimal zone pattern ought to be. I'm going to go with a metal, and I'm going to select the metal. Now, normally it would be some kind of automotive grade steel material like this, and I can view that material, or I can pull it up. I can see stress allowables in English units or in SI units, megapascals, and you can see here a little bit about our database of materials. But for this example, I'm going to use something that's a little bit more generic. It's a material that has reduced material properties. It's basically representative of a generic aluminum. So this is the material I'm going to select for this example to start off with. Now you could come in here and change the minimum gauge thicknesses and the incremental thickness that it's allowed to size to. I'll go with the default values shown here. Here's some of the analysis methods it's going to do in the early stages of the optimization. I'll kind of skip over this because I will come back to it later. Now what you're looking at is the Fem Inspection part of the software. So the first step would be to be aware of what the element forces are. I'm going to turn the boundaries off, and I'm going to reduce the number of significant figures on the right here. And basically, you're looking at the membrane NX load. I can look at the NY load, NXY load, the moments, and any of these values in this manner. If I zoom in like this and move it over, notice that this is the load case called torsion left up, and this is torsion right down, and you can see the load reversal here in this piece. So again, that's a compressive load. The magenta, the red is a tensile load, and I'll go back up and you can see it in this fashion. So let's say we're happy with the loads the FEA solver is presenting to us. Material axes are very important, and this will be a composites example, so you do want to know in which direction you're intending the unidirectional ply to be oriented. And for the aerospace guys, this is not your traditional tape material. These are like wide, 4-foot wide unidirectional layers where the part shape is cut out. So this would be indeed the zero axis for this part. Okay, so taking the mesh back away here, and one last thing would be the element normals. So if I zoom in again, you can see all the normals are pointing consistently, and that's for the stacking of the laminate. You want to know that your first ply defined is the same throughout the part. Now this is the fun part. Next, this is where I'm going to be doing the actual optimization. So let me pull this back over here so you can see it better. And I'm going to say not use the existing property zones defined by the preprocessor, but instead I want to allow our software to redefine those. So you can see it's extremely fast. It's done. The weight of that part is 1.7.4 pounds. This is a gauge thickness of the metal here. So you can see the pattern. So the red is a thicker area, and as we go through the legend on the right, the magenta pinkish color is the lighter gauge thickness for this part. Now if I continue through the process, what we're looking at now is the ability to say what elements ought to be grouped together for manufacturing purposes. So right now we have 7 different gauge thicknesses, but they're kind of spread throughout the part here. It could be quite difficult to make. As I move my cursor to the right, I go from minimum weight to minimized thickness boundaries. Here, currently have 7 zones for 1.75 pounds, and now I have 3 zones for 2 pounds. Let me also, you'll see this a lot today, so I need to describe what's happening. So basically, we have 3 unique gauge thicknesses, but again, they're kind of spread throughout the part. The continuous optimization here now identifies each of these as being separate. So you can see several places where when I go through here, they have this, like this is 3.85, 3.85, 3.85, 0.33 is 0.33. And so, but the difference, there is 0.33 thicknesses here and here, but a different thickness in between. So basically, this is what the tool's purpose is here, is to be able to come up with these proper collection for reduced manufacturability effort, and you can play with it interactively in this manner. What I want to do next, and keep in mind that we're looking at somewhere close to 2 to 2.1, 1.9 pounds for this part. I'm going to go back to the beginning of the process. I want to change it from a metallic to a composite. So that's a very substantial change in the software. So we have to go all the way back up again. And that has a lot to do with the design criteria for composite being more than they are for metal. Again, I do not want to use the FEA solver. Now notice the laminate is checked, and I'm going to select a unidirectional tape material. I'm going to pull the form up so you can see and compare it to what you saw earlier with metal. So this is a lot of tabs here now for the composite. These are the moduluses here in English units. Here are the stress allowables. I do want to point out we have things such as correction factors here. Because it's a demonstration example, all the corrections are set to 1. But this is very important for things like co-cure and AFP and things of that nature. And then we also have laminate allowables. So I have compression after impact, open hole compression. If you're familiar with this, good. If not, that's okay. But I wanted to make people aware of the depth of which we can define material allowables. So I'm going to choose that material. I'll go to next. I'm using, for now, traditional aerospace rules. So I'm requiring at least 10% zeros, 20% 45s, and 10% 90s. And my min gauge is 4 plies. In aerospace, we would normally require it to be symmetric, but I'm going to not enforce that, but I will enforce that all the laminates are going to be balanced. And let me also point out here that I've defined a full assembly ply, a 0. So you can add any number of plies or any material you want to on the outside and the inside of your laminate. Now that it's a composite, you can see there are more failure criterion. By default, we have Sci-Han for a ply-based, and we have just one open hole compression laminate-based allowable selected. We can go through this quickly because nothing's changed here. It's the same FEA loads. And now I'm going to optimize this part as a composite. And now you can see the weight is 1.09 pounds. And you can see things like the ply count zeros, ply counts of 45s, and 90s, and things of that nature. There are a lot of different ways to do this optimization. And you can see what's happened is I've selected a parameter to give me more blended and smooth results. So now you're looking at for the red is the number of 90s. This color is for the number of 3 for the number of 90s and 2 for the number of 90s. And the 45s like this, and the zeros like that. And this is your total ply count here. So you're wondering, now it's much more complicated because now the patterns are not just based on a single value called thickness. Now it's based on, to be truly optimum, you need to, these elements that you associate to a property should be defined based on the individual counts of zeros and 45s and 90s. And if I move this to the left and I'll start the process, we can see these are some of the optimum zones, and I move it to the right, and you can see these values here. So now we're at 7 zones at 1.15 pounds, and before the legend was showing gauge thickness, now the legend is actually showing you ply counts, so 5 plies, 7, 8, 9, all the way down to 13. And in the parentheses, what that is 1, that means 1 0, 2 45s, and 2 90s. So that's what the code is. And I can do the same thing now by separating the zones, and there's 64. So you say, well, that's a little bit too much for my manufacturing purposes. There are 49. Now we're down to 16, and it's 1.3 pounds. So you may say, well, that looks pretty good to me here. Maybe I could make that part. I'm willing to pay that additional weight to make it a little bit easier to make. So that's, in the metal example, I didn't go this far, but now I'm going to go to the next step, which is basically to accept and to establish these zones. So now you can see the zones here. And now you see the bold line that basically is informing you that the original properties from the import are no longer valid, and your new properties are now the established grouping of elements. So as you can see here. Now, what I want to do is continue on. So it's done optimization, and at this point, you could sequence. So let me show you what that means. So I will hit this icon here. It's finished the sequencing process. So let me show the table. This is kind of now, from a more of an engineering perspective, this table here could be of value to people. If I click 15, you can see that this area right here that has this definition has basically a 0. We'd required 0 on the outside, and 2 45s, a 90, 2 more 45s. So you can see, indeed, it's not symmetric, but it is balanced. So we do have the same amount of positive and negative 45s. And if I click this, you can see a similar situation. Here we have a 0 in the middle. This is probably not the easiest way to see such data. So I can go to a flattened pattern view like this, and I can see the same data this way. What I want to do is to open this dialog here and turn off the mesh. And what I would like to do now is to look at the data one more time. I want to use sort of a random color scheme. This is probably easier to see. So what does this mean if I were to go and look at the part in this manner? Basically what you're looking at is the way in which we envision that this part's going to be laid up. So that's the first ply, second ply, third ply, fourth ply, fifth, sixth, 7, 8, 9, 10, 11, 12. You can get the idea basically. So you can see it as a manufacturable solution that we've defined here. And we can see this kind of data in different ways. You can see it in this manner. So let me also bring out just one other tool we have. I can create a section cut. I use that pencil icon to draw a line, snap a line this fashion here, and say OK. And I've created a cut plane, and then I can say to show the cross section for that cut plane. So you can see here, this is the laminate here as is currently being optimized. and that's a ply drop at that location. And that white spot means basically that we went through a hole here. Let me go back to this guy here. And what I'm going to do is to try to take a snapshot of the current solution. Let me try that again. Okay, so what I'm going to do is to make a static image of the current solution. I've got that to the left on the second monitor. I'm going to go to full sequencing, move this guy all the way to the right, and resequence. And now what's happening is the software is doing a trade. It's going to trade, you know, laminates that are probably a little bit heavier, but the new part's going to have, say, fewer ply drops, less ply cuts, probably essentially will have fewer global plies, and from a stress perspective, it'll have fewer plies that are not interleaved. So that's the issue with, say, the interlaminate shear stresses. And so this is the new design here, and move it over to the left, and I'm going to compare it to the previous design here that we made a snapshot of. And so we went from 19 global plies to 10. We had previously we had 47 drops and adds. Here we have 16. Here we have a really good solution. We don't have any zero plies that are not interleaved, where over here we had 4. And finally, we had 295 ply cuts. Over here we have 184. And the weight went from 0.86 to 0.962. So the idea behind the tool then is to allow you as an engineer to sit down with your manufacturing guy and you decide how you want to compromise between the lightest possible weight and a more easily produced part. At this point, you can play with different designs and different sequences. There are many proposed here as I go through this list here. At some point, you're going to say, this is the one I want to use. And we had seen that one, so let me go back to that. And I'll go to next. Do I want to save this change? I do. So I'm committing it. So now I'm basically what I'm doing is I'm taking optimum results we saw before, and now you manually modify those optimum results. But the key to it is we still have a positive margin of safety. So we have no red, no orange margins of safety. We have all positive margins of safety. And you can plot things like ply percentages and ply thicknesses and so forth. All right, so what I want to do next is to very quickly now go back to my analysis criteria, the Fem import. I'm going to go to FEA setup. This time I do want to include the solver, test it, passed, and I want to go to my analysis criteria, and now I do want to put in a deflection limit. And I don't know what, I have to go to my PowerPoint to see what the reference grid is. 14605 is my reference grid. So I'll put that in here. And I want to limit it to 10 inches deflection. Before I kick off the process, let me go to data, displacements, translation magnitude, get a proper color scale. And we can see over here in this region about somewhere close to 21 inches of maybe 20 inches of deflection here. I can also see this by going to plotting it in this manner here. So you can see the undeformed shape mesh and the deformed shape mesh, okay? So basically, why I'm going to do this, I'm going to also say that I want the optimizer to consider foam sandwich here. Maybe have 0.01 as a bond weight. And I want to choose a foam material. Here I'm going kind of fast and say next. Now, the design criteria says, oh, I know what you want to do with the laminate, but now you added a new thing called core. What is the min and max bounds of the core and what increment? I'm going to use default values here. Here, shear crimping and shear stress and things crushing is now relevant because we have core. I'll skip over that. And now I want to try new optimization zones because I'm adding foam to the solution and I'm adding a stiffness criteria to the solution. So my previous optimum patterns are probably not relevant. And notice on the left in the tree, we have these things called pass 1, pass 2, pass 3. The software is automatically updating the FEM with new optimum results, submitting the FEA solver, waiting for the solver to complete, reading in the stress resultants from the solver, doing another optimization, is reading the displacements from this solver, and is determining what part of this structure is most efficiently stiffened to reduce deflection, and is it 0? Is it 45? I mean, what ply orientation is the best to use for this solution? So let's go first to core thickness here. And let me turn off the displacements because that's a little bit, oh, well, we want to see what the magnitude is first. So you can see here in the area that's probably in yellow, orange, is about 10 inches. So it met its target deflection criteria. I do want to point that out first. Let me turn off the deflection now so we can see it better. And we want to see first the, say, ply count 0 solution. So you can see because we've added core, it needs a lot less ply material. So we go from 1 to 2 plies of 0. And for 45s, we go from 2 to 6. And for 90s, this is our solution. And let's look at the core thickness. So this is the core thickness. And you can do a lot of things at this point. You can accept that. You can say at most of my core thickness is 0.4, and I would come back to design criteria maybe and just specify 0.6 as my required. So it's either going to be solid laminate or 0.6 core, nothing in between. You can do these kinds of things. Anyway, I think what I'll do is 45 minutes. I had a kiteboard example, and it was really cool to show. I want to leave time for Bertram to do his bike example, so I'm going to basically skip over the kiteboard here. This is, the loading, landing loading here. This is the deflection. You can see real quick here. If I were to go to looking at the optimization here, you can see where the optimization is putting in additional 0-degree plies here to handle that deflection in an optimum sense. And this is the mesh for this particular model. Maybe in a future webinar, we can talk more about the kiteboard and the engine IFS and wind blades and things of that nature. But what I would like to do at this point is now have my colleague Bertram spend the last 10 minutes here showing what he has for the bike. So you go ahead.
Okay, thank you, Craig. Hi to everybody from me as well. I'm Bertram Stier from Collier Research, and I would like to share with you the optimization of a bike frame today that I prepared. Here's this bike frame structure that we have. You see the elements at the undeformed shape and an impact load, a frontal impact, horizontal frontal impact load in this point of time. I would like to jump into this optimization after I've already imported the FEA and I've chosen my materials that I want to use, which is just a unidirectional carbon fiber reinforced plastics material. And I want to go, when we are optimizing, we want to basically answer 3 questions, as already pointed out by Craig. We wanted to know where are the best potential ply boundaries, how much material do I need, and in which direction does this material need to be. And, well, we've defined here 8 different load cases. Again, this first one is the horizontal impact, in which we also want to minimize the deflection. So at this load case, we fix these rear points here, and we apply a load at this node, and we want to minimize the deflection in this direction of that node. So as you can see, the load introduction to the structure that we optimize can be done using other elements like bar and trusses. It does, yeah. Of course, we automatically take care about the strength of the entire structure for all the different other load cases that we've defined. For instance, the torsion of the fork, or a drop, a landing, or an ultimate load at the seat post when the rider is bumping into its seat and is applying a huge moment here. And, well, then after we've imported the FEA, we need to bring together all the different ingredients we need to define our requirements for this optimization. So in the end, of course, strength is always a mandatory requirement. Stiffness, however, is basically a requirement that can be set or not, depending on whether you want to have a structural stiffness target or not. However, the first stage is here to define design criteria. And for bike manufacturers, we really don't care how much zeros, how much 45s, and how much 90s we have in the entire structure. But probably, since you want to have more or less a little bit more damage tolerant design, you want to have at least 4 minimum plies on the entire structure. So I'm going to put 4 minimum plies in here. But which direction, which material direction the plies are defined is completely free. Furthermore, we can also, again, define whether we want to have symmetric and or balanced laminates. We can also create sub-laminates if we wanted, but at this point, we don't even need this. So I uncheck all of these boxes. Now, this is a little bit more interesting because at this point, we definitely want to have a stiffness requirement. So we want to take care about the membrane stiffness requirements and the bending stiffness requirements. And we also check each and every point to meet the strength requirements for the Tsai-Han interaction criterion. Of course, you see that there is a multitude of different failure analysis methods defined that can be checked and could be simultaneously fulfilled all at the same time. This is the form where I define how many iterations I want to use to meet my deflection limit target, and this is where I also define which grid should be limited in which direction, and that's what I put in here. That's basically all I need to do to define my stiffness requirement. Then I hit next. I can once more go through all the different load cases that I have, and through all the different internal section forces. But Craig already covered this topic. I want to check once more the fiber directions that are defined, which is pretty interesting here, where the joints are, and also the fiber, the normal directions of the shells. And those look good to me. So right now I'm trying to optimize the ply boundaries. And for this purpose, I want to switch off the undeformed shape and hit next. And as you can see, this finite element model has about 30,000 elements, and we can still live demonstrate it because it's so fast. Right now we are trying to set requirements, and after the first run, we can already look at the number of zeros that we have over our entire structure, distributed over entire structure after the first strength sizing. Then of course, since we got rid of a lot of material, the deflection in the first pass increases tremendously because we saved so much material and so much weight. This is what we want to show right now in a short time. Here we can see that we have some regions where we have not a single zero, and this would be the deformation. Now, as already said, since we saved so much material due to strength sizing only, the deflection at this point increased. And now we need to find out the most intelligent, the smartest locations on where we put the zeros to minimize this deflection at that point down here. And as you can see, we already saw that this is pretty much a bending member, the top tube, and we can use this bending member to minimize the rotation of the head tube, which will then minimize the deflection of the front fork or the front axle at this point. And so here we have a pretty big zone at the top and bottom that has already 3 zeros, but only a small section that has 4. So now I want you to pay attention to what happens to the front fork. As we could see, we minimized, or we already minimized the deflection here until a certain point, and we found out that we need to increase the zeros at this region and down here to minimize the deflection. And we can basically interactively look at this, how Express finds out these ply patches, which are the smartest material directions which we want to choose, and so on and so forth. And we can also look at a file that allows us to follow how we converge to this deflection. Of course, this is not a one-step process. This is an iterative process that we are following here. And as we can see, in the first iteration, we got down from nearly 0.8 inches to 0.5 inches, but our target was 0.3. and you will see in a second that once we've finished this iteration, that we also meet our deflection limit. Now, for the guys who were sitting there with a stopwatch, I did this as well when I prepared for this session, and the whole optimization until this point here takes about 3.5 minutes. So an entire structure with 8 load cases and a stiffness deflection target takes about 3.5 minutes. Here we already can see that the ply count changed as well. We have a better gradient here that we propose here and also there. And very interestingly, down here there is also a 0, but we also want to have a big number of 90s around this section here, and this is in the end to prevent this local buckling or kinking of this down tube down here. As you can see, we also propose very smooth and nice looking, very effective ply boundaries that are very manufacturable, as you can imagine. We can also look at the 45s here, and we can see that in these regions we don't need 45s, but here, basically, in order to prevent or to increase the torsional stiffness, that's where we want to put our 45s. And up here, we need the 45s to introduce the load that's coming from the bearing cups down to the down tube, and also from the lower bearing cup to the top tube. We want to have fibers in this direction at these positions, left and right as well. Of course, we want to check whether or not we met our deflection limit, and as you can see, we set the deflection limit 0.3, and that's what we mean. Of course, this is in a certain tolerance. Then, as we've seen this, we try to overlay these proposed patches of the individual plies and the ply numbers, and we want to optimize our ply shapes, our general ply shapes. And this is where you can also sit down with your manufacturing engineer, and it's completely up to you how fine you want to resolve the gradients of your requirements that we've set in the previous steps. That means that if you have a certain requirement at position A, maybe up here, and you have another requirement in a position down here, you can basically define with which resolution you want to resolve the gradient in these requirements, and this will basically define the number of ply cuts that we propose. Now, either you have a genius manufacturing capability, then you can easily manufacture this bike, but maybe you don't, and your manufacturing engineer says, there is no way I can make this bike within our cost target that we have. Then you can say, well, okay, I'm willing to pay with weight that we minimize the ply boundaries or reduce the number of ply boundaries until a certain number of plies that your manufacturing engineer is willing to produce. And since it's so fast, you can really sit right next to each other and discuss whether or not this is reasonable to manufacture or not. Well, then after that, we basically just select these zones and size these zones, and that's the part you already have seen with the torsional stiffener Craig already presented. You have the exact same capabilities later on, where you can see the stacking and so on and so forth for each and every ply, for each and every patch, for each direction that we have. So basically, we answered all the 3 questions that we have, and it's really easy to follow through this wizard. So you also don't need an expert in optimization to perform this laminate optimization for you. I guess that once you've seen this already twice, you could probably already do it yourself. And at this point, I want to give the stage back to the plenary.
Okay, great. Well, thank you, Craig. Thank you, Bertram. We are past our 1 hour, so those of you who need to go, we completely understand, and thank you for your attendance. We are going to try to answer at least a few questions for those who want to stay on, and we'll get to that in just a moment. Get to the questions here.
Oh.
Okay.
One question we had was, I showed a foam example, and the question was, can Honeycomb Core, your typical Hexcel materials, be used? And I didn't show that example, but of course they could be. So in an aerospace application, the software is capable, you can put in different densities like 3.1, 4.5, 6.1, PCF type cores. And this is a scenario where you have high-end out-of-plane shear forces, QX, QYs. As it does the optimization, it will tell you what location needs to be what density core. I should mention the fact that when we create these FEM property zones, the priority first would be panel concept. So basically, it's going to try to determine what part should be unstiffened, solid laminate, what part ought to be sandwich. Second of all, we put a priority on core thickness. So basically, we know from a manufacturing perspective, it's quite challenging to make a part that has a variation in core height. And so it's easier to actually change core density than it is to change core height. So number 3rd would be core density, and then 4th, the least priority then would be the laminates themselves, because it's considered a little bit easier to find and remove and add plies to meet your required stiffness and strength. One question, I guess, came from someone who's used to using our Pro product. In Pro, we define or we refer to these zones as components, structural components. The structural component in Pro is the same thing as what we call the Fem zone in Express. We have some more questions, but I think what we'll do at this point is to go ahead and allow you guys to email us. I think the contact information is available to you, and you probably would appreciate a more formalized response in any case. So with that being said, we're going to go ahead and end the call now. Again, we thank you for your attendance, and we look forward to hearing back from you. Thank you.
Thank you, everyone, for